In this section, we're going to go over some method of counting and how we could use them to compute probabilities and to solve real-world problems. So to begin, I want to talk about something called the fundamental principle of counting. So suppose we have an experiment that consists of 3 steps, and our goal is to find the total number of outcome of our experiment. And let's say we know the total number of outcome in our first step, second step, and third step, and they represent A, B, C respectively. Well, then we can compute the total number of outcome by multiplying A times B times C. And this is the fundamental principle of counting. For example, license plate numbers contains 3 letters and 3 digits for a specific state. And we want to know how many different ways we could make a license plate. We know we have to multiply 6 numbers, and the first 3 are going to be letters, and the last 3 are going to be digits. But we know that there are 26 letters in the alphabet, so the letters would be 26, and for digits, there would be 10, because they go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, so it would be 10. When we multiply all these values, we get 17,575,000 ways we could make a license plate. Now let's consider tossing a coin 3 times, and we want to find the total outcome for this experiment. We know that each step has 2 outcomes, and there are 3 steps in total. So that means the total outcome will be 2 times 2 times 2, or 2 to the power of 3, or 8. Next, I want to talk about something called factorial. So whenever you see this symbol here in mathematics, this represents a factorial. And for any positive integer n, this number here is pronounced n factorial. And this is equal to the product of all the integers from n down to 1. So n factorial will be n times n minus 1 all the way to 2 times 1. So for example, let's evaluate some of the following. 5 factorial is just going to be 5 times 4 times 3 times 2 times 1, which is 120. And 12 minus 4 factorial, we know that 12 minus 4 is just 8. So 8 factorial will be just 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, which is 40,320. And notice that factorial gets really big really fast. But what's 0 factorial? Well, it's actually equal to 1. And factorials are really good to compute every possible outcome in your experiment. So for example, let's say you're a business owner and you have 5 locations to establish your business, and you want to know how many different ways that you could rank these locations. Well, there are actually 5 factorials way that you could possibly rank this, or 120 different ways. One thing I want to talk about is permutation. And another word for permutation is ordering, which is going to make sense in a bit because in dealing with permutation, here order matters. So permutation gives the total number of ways that we can select some amount of object R from a total of n object in such a way that order of the selection is important. Or in this case, order does matter. And some of the notation we're going to use is little n, big P, and then little r. The way I like to say this is n pick r, where P is pick. And we're going to use something called the permutation rule of counting. So n pick r is just n factorial over n minus r factorial, where n, again, is just the total number of object, and r is the sum amount of object that you selected from the total number of object. For example, let's say a club has 20 members, and they have to select someone to be president, secretary, and treasurer. We want to determine every possible outcome, and notice that here order does matter because a person can't be president twice. There's actually 2 ways we could figure this out. we could use the fundamental principle of counting. So this will be 20 times 19 times 18, because every time we pick someone, we lose a person. So this will be 6,840. But we could also use permutation to figure this out. So in this case, out of the 20, we're picking 3, and order does matter here. So we could just plug it into our formula, and you should get 20 factorial over 17 factorial. But let's say your calculator can't compute this because it's too big. You could do is 20 times 19 times 18 times 17 factorial over 17 factorial, and then just cancel them out. So this will be 20 times 19 times 18, which should give you the same result as we did in the other example. But what if order doesn't matter? Well, then we use something called combinations. So here, combination gives the number of ways that we can select some amount of object R from a total of n object. And again, with combinations, order doesn't matter. The notation that we use is n, little n, big C, little r. And this is read as the number of combination of n element, select r at a time. And similarly with permutation, we have a combination rule of counting. So this here, to compute this, will be n factorial over your r factorial times n minus r factorial. So for example, let's compute some of the following. So here, 7 will be our n, and 4 will be our r. So if we plug into our formula, this should be 7 factorial over 4 factorial times 3 factorial, which is 35. And here, we do the same thing. But in this case, 6 is our n, and 3 is our r. So if you plug the values in, it should give you 20. Next, you want to know how many combinations of 4 objects are there taking 2 at a time. So you could say 4 choose 2. So that's another way you could say it. So if you plug in the values, this should be equal to 6. Next, let's say an ice cream parlor has 31 flavors of ice cream, and Jane wants to buy 2 scoops of ice cream. So here, there's 32, choose 2, which would be 31 factorial over 2 factorial times 29 factorial, which is 465. So in words, there are 465 different combinations. So far, we learned about 3 different methods: the fundamental principle of counting, permutation, and combinations. But how do I know which one to use? Well, hopefully this little chart might help. So if the experiment consists of a series of steps with various outcomes, then use the fundamental principle of counting. These types of problems typically do not involve selecting a certain number of the object and instead involve using all of the object. But let's say your experiment consists of selecting some amount of object and the order of this does not matter. Then this gives you a clue that to use combinations. And just a little note here, no reputations are allowed. And let's say your experiment consists of selecting an object and order does matter. Then this kind of gives you an idea that we use permutation. And again, no repetition is allowed. So let's say Sophia has 3 tickets to a concert and 4 of her friends wants to come. So what she does is that she decides to randomly select 2 of her friends at random. So we want to know how many ways can she select her friends. So there are 4 different friends, but only 2 could go. So this kind of gives you an idea that we're either going to use permutation or combination. But since the order of the friends doesn't really matter, this gives you an idea that we're actually going to use combination. So the order of how the friends are chosen does not matter. So that's why we use combination. So then this will be 4 choose 2, which should be 6. Next, let's consider another license plate number. But in this case, we're going to consider a California license plate number. And with California, it goes a number and then 3 letters and then 3 numbers. But since there's 26 letters in the alphabet and there's 10 digits, we know this will be 10, 26, 26, 26, 10, 10. So this, we are using the fundamental principle of counting. So if we multiply these values, we get 175,760,000. And what this number represents is how many different ways we can make a license plate number. So it's a very big number. We could also use some of these counting methods to compute some probabilities. So for example, let's say 30 people attended a certain event and 5 will be chosen at random to receive a prize. And here, order doesn't really matter. So we could say that out of 30, we choose 5. So this should be 30 factorial over 5 factorial times 25 factorial. But let's say your calculator can't handle these big numbers. So what you could do is that 30 factorial could be written as 30 times 29 times 28 times 27 times 26 times 25 factorial. And the reason why we want to do this is because we could actually cancel out the 25 factorial. And if we do that, then the computation will be a lot easier. So this should be 142,506. And what this number represents is how many different groups of 5 people can be chosen. And we're going to use this number to compute some probabilities. So here's a little note that we're able to use counting to compute probabilities. Okay. So consider the same problem, but with some additional information. Now we know there are 12 men and 18 women in this event or this party. And again, we're choosing 5 random people to win a prize, so order doesn't matter. We want to find the probability that all the prize winners are men. So in other words, the probability of all the winners are men. This is going to be the number of outcome, the total number of outcome where all 5 people are men, divided by the total number of outcome. But we already know the total number of outcome. We just did it in the previous example, which is 142,506. So we already know the bottom number. It's the top number is what we have to look for. So out of these 12 men, we want to know all the possible 5 outcomes. So this is 12 choose 5. So you just put this in our formula, and this should be 792. And now we could just plug in this value up here. So then it should be 0.0056, which is a really small number, which makes sense because the probability of all 5 winners are men is really, really low. Next, we want to find the probability that at least one prize winner is a woman. And there's actually a lot of ways we could figure this out, but the easiest and best way is using the rule of complement. So if you remember, the probability of A is just 1 minus the probability of A complement. Here, our event A is just at least one prize winner is a woman. So here, the probability of at least one prize winner is a woman. It's going to be 1 minus the probability of no woman is the prize winner. But we already know this probability because no woman is the prize winner is the same as all the men were a prize winner. which was 0.0056. So if you plug in the values, you'll get 0.9944, which is a really high probability, which makes sense because you're bound to choose at least one woman from the 5 winning people.